Dear students, this paper titled as Metal Pi Complexes and Metal Cluster is divided into two sections and we will be studying these sections one by one. First of all, we will begin with the metal pi complexes which constitute the metal carbonyls. Their structure and bonding we will study in detail. Then we shall discuss about the vibrational spectra of the various metal carbonyls by taking specific examples, and this we shall deal for the bonding and the structure elucidation. We shall also study the important reactions of metal carbonyls, how the metal carbonyls are prepared, what is the bonding in them, we will take some examples and we shall discuss their structures and give you the 3D idea about their structures. And after this we shall study some important reactions of the transition metal nitrosyls, dinitrogens and the dioxygen complexes. And then in the first section we shall also study the tertiary phosphine as a ligand in the metal pi complexes. So, after studying this metal pi complexes, the next section we will take is the metal clusters. In metal clusters, we shall be dealing about the higher boranes. You are already familiar with the borane elementary treatment. We will start with that, but then take the higher boranes. Then what are the carboranes, their structures and different properties associated, the metalloboranes and the metallocarboranes. Then we shall focus our study on the metal carbonyl and halide clusters and the corresponding compounds. We shall also study how the metal-metal multiple bonds will be there, and so this section 2 will be dealing about the metal clusters. So, dear students, let us begin with this module, and here we shall be understanding the pi acceptor ligands are a special case of ligands which contain pi bonds. The anti-bonding type pi orbitals in these ligands, if vacant and of comparable energy, may receive electron density from the filled metal orbitals with which the ligand is coordinated, and this we will understand with the help of visuals. And because of this, the ligand may act as sigma or pi donor of the electron density to the metal ion, and at the same time it also acts as a pi acceptor ligand. So, if you look for pi acceptor or the pi acidic ligand, they form two types of bonding with metal d orbitals. One is that it will be forming the filled pi 2pz bonding molecular orbital, and another is it will be involved in the vacant pi 2pz star anti-bonding molecular orbital. We shall also understand that in the metal carbonyl complexes, the direct bearing of the pi back donation is observed on the metal carbon bond distance that becomes shorter as compared to that of a normal metal carbon single bond distance, and further that the metal binds to carbon and not the oxygen, and it is because the ligand HOMO is the carbon and not the oxygen lone pair. And the reason for this is that the oxygen is more electronegative and therefore its orbital have lower energy, and that is why the metal will bind to the carbon and not to the oxygen. If we look at the dipole moment of the free carbon monoxide molecule, you are aware that it is close to 0. In this module, we will also study about the nomenclature of the metal carbonyl complexes. The metal carbonyls are nothing but the coordination compounds, and hence their IUPAC names will be written as per the rules approved for the nomenclature of coordination compounds, and the elementary idea you are already familiar, but we shall take some examples and see how the metal carbonyl complexes will be given the IUPAC nomenclature. Going further, we shall see that the metal carbonyls are classified into different ways, and on the basis of metal carbonyls we can see they are homoleptic metal carbonyls. They are the metal carbonyls which contain only carbon monoxide molecule as the ligand. They are called as the homoleptic metal carbonyls, and under this the examples you can consider are the nickel carbonyl, the iron carbonyl, the chromium carbonyls and so on. They can also be classified as heteroleptic metal carbonyls, and as the name hetero suggests that these are the metal carbonyls which contain some other ligands also in addition to the carbon monoxide. So, carbon monoxide is not the only ligand as it was in the homolytic metal carbonyls. So, here we can consider the examples of the cobalt complex where the CO4 is there and H. So, you can notice that H is the additional ligand here. So, this is the tetracarbonyl hydrogen cobalt. Similarly, the other examples are listed here. You can see the RHCO twice Cl2. So, here the carbon monoxide, there are 2 ligands and there are 2 chlorine ligands. Similarly, you have this example of RHCOH triphenyl phosphine thrice, that is there are 3 types of ligands here. You have carbon monoxide, then you have hydrogen as hydride and you have the triphenyl phosphine. Similarly, you have this platinum complex where 2 carbonyl ligands are there and 2 chlorine ligands are here. So, homoleptic is containing only the carbonyl as the ligand, and heteroleptic metal carbonyls are those which have carbonyl as ligand, but they have other ligands also in the complex. Another way of classification. So, this first way of classification was on the basis of the ligand nature, that is the carbonyl, whether it is the same type or different type. Another type is on the basis of number of metal atoms which are present per molecule, and on the basis of this it is further categorized as mononuclear metal carbonyls or the polynuclear metal carbonyls. When we say mononuclear metal carbonyls, these are the metal carbonyls which contain only one metal atom per molecule. For example, you have nickel carbonyl, iron carbonyl, chromium carbonyl. So, you can see here in all of them there is only one metal atom. There is one nickel, there is one iron, there is one chromium. On the other hand, when we say polynuclear metal carbonyls, as the name itself is suggesting that these are the metal carbonyls which contain more than one metal atom per molecule. For example, Mn twice CO10. So, you can notice here there are 2 Mn atoms, then Fe2CO9, that is you have di-iron nonacarbonyl, and here you can see there are 2 iron atoms. Similarly, you have Fe3CO whole 12 where you have 3 iron atoms, and CO4 CO12 there you have 4 cobalt atoms, then Ir6 CO16 you have 6 iridium atoms and so on. So, all these are the polynuclear metal carbonyls where there are more than one metal atom which is present per molecule in the complex. Polynuclear metal carbonyls are also further classified into homonuclear and heteronuclear. So, this will be again on the basis of that whether it has only the carbonyl as the ligand, then it will be homonuclear, but here there will be more than one metal atoms which are there in the complex. So, for example, you have Mn2CO10, Fe2CO9, Fe3CO12, CO4CO12, Ir6CO16. So, all of them notice they have more than one metal atom and they have only the carbonyl as the ligand. So they are also classified as heteronuclear metal carbonyls, and as the name suggests, these are the polynuclear metal carbonyls in which more than one metal atoms are present. For example, MnReCO10, you can see there is Mn and Re. Similarly, MnTcCO10, we have Mn and Tc as the metal atoms. And another way of classification is done on the basis of charge on the coordination sphere. And on the basis of charge on the coordination spheres, these metal carbonyls are classified into three types: neutral metal carbonyls, cationic metal carbonyls, and anionic metal carbonyls. Again, here the name is very clear what we mean by them. The neutral metal carbonyls are those in which there is no formal charge on the coordination sphere, and here you can consider the examples like nickel carbonyl, iron carbonyl, chromium carbonyl, and you can notice there is no formal charge in any of them. Then further we shall see, after understanding this categorization, that the process of pi acceptance of electron density of a ligand from the metal ion in a complex is an extremely important phenomena in these metal complexes, and this will give rise to a number of chemical properties and applications. The pi back donation of electron density results in variations in the bonding properties of the ligand, such as bond energy, and this change in bond energy can be detected by various spectroscopic techniques, and therefore the intensity of charge donation from metal to the ligand can be estimated in order to quantify the various properties of the metal complex under consideration. And few examples, if we talk about the pi acceptor ligands, are ethylene, the cyclic pi systems such as cyclopentadiene and carbonyls, etc. So dear students, let us summarize what we have learned in this module. We have discussed that the pi acceptor ligands are a special class of ligands which contain pi bonds. The anti-bonding pi orbitals in these ligands, if vacant and are of comparable energy, may receive the electron density from the filled metal orbitals with which the ligand is coordinated. Therefore, the ligand may act as either sigma or pi donor of the electron density to the metal ion, and at the same time it acts as a pi acceptor ligand. We have also seen that pi acceptor or pi acidic ligand forms two types of bondings with the metal d orbital, that is, there will be filled pi 2pz bonding molecular orbital and the vacant pi 2pz star anti-bonding molecular orbital, and this we have understood with the help of proper graphic and visuals. We have also studied that in the metal carbonyl complexes, the direct bearing of the pi back donation was observed on the metal carbon bond distance, which becomes shorter as compared to that of the normal metal carbon single bond distance. And it is this clue which is giving you a hint about, yes, there is a back bonding also which is reducing this particular bond length. We also studied that metal binds to the carbon and not oxygen, and this is because of the ligand HOMO is the carbon and not oxygen lone pair. And we have also understood the reason for this, that it is because oxygen is more electronegative than carbon, and so orbitals will have lower energy, and hence the metal binds to the carbon and not to the oxygen. This is very important thing to remember. We also studied that the dipole moment of free carbonyl molecule was close to 0. In this module, we had also studied about the nomenclature of metal carbonyl complexes by taking certain examples, and I hope you will be able to now write the IUPAC nomenclature for any given metal carbonyl complex. The metal carbonyls are coordination compounds, and hence we have seen that their IUPAC names are written as per the rules which are approved for nomenclature of the coordination compounds. We also studied the various ways of classification of metal carbonyls, that is how the metal carbonyls are classified on the basis of the carbonyl ligand. Then if it is only carbonyl ligand, then they are classified as homolytic metal carbonyls, that is only the CO is present as a ligand and no other ligand is present in them. They are also classified as heteroleptic metal carbonyls, and here as the name suggests hetero, there are more than one, that is in addition to carbonyl there are other ligands also present, and these ligands may be the hydride, the chloride, the triphenyl phosphine and so on, and we have considered some examples to understand all this. We have also seen that this classification of metal carbonyls can also be done on the basis of number of metal atoms which are present per molecule, and here we have seen that they are classified into either mononuclear metal carbonyls or polynuclear metal carbonyls. And in case of mononuclear carbonyls, as the name suggests, there is only one metal atom, and we have considered some examples to understand. And in polynuclear metal carbonyls, there are more than one metal ligands, and under this also we have studied that these can be of the same type, that is the metal atom is of same metal element, then they are homonuclear. For example, 2 Mn or 2 iron or 3 irons or 4 cobalts or 6 iridium, we have considered examples. And they can be of heteronuclear, that is they can be combination of more than one metal atoms like manganese with rhenium or manganese with technetium and so on. And we have also studied that another way of classification is on the basis of charge which is there on the coordination sphere, which contain the carbonyl as ligand, and based on this they can be neutral, obviously as the name suggests they have no charge. They can be cationic, and here again the name is very clear, they are the ones where the coordination sphere will have the positive charge on them, or anionic, and they are the ones where there will be the negative charge on the coordination sphere. After this, we have studied that the process of pi acceptance of electron density of a ligand from the metal ion in a complex is an extremely important phenomena in metal complexes, which will give rise to a large number of chemical properties and applications, and we shall be dealing with some specific examples in the subsequent modules. The pi back donation of electron density results in variations in the bonding properties of the ligands, such as bond energy, and this change in bond energy can be also detected by various spectroscopic techniques. We also studied some examples of pi acceptor ligands, which are ethylene cyclic pi systems such as cyclopentadiene and carbonyl, etc. So, dear students, I think this first module is giving you the very elementary idea about the metal carbonyls, their nomenclature, their classification and some basic bonding ideas, and we will be going into more depth as we go into the subsequent modules.
This module will help you out to learn out what are metal carbonyls, how to classify them and their nomenclature, what is pi acidity and pi ligands, and properties in terms of symmetries, infrared frequencies, etc. The main characteristic feature of T-group transition metals is that they have an ability to form complex compounds with a variety of neutral molecules, such as carbon monoxide, isocyanide, substituted phosphines, arsines, nitric oxides, and various organic molecules with delocalized pi orbitals such as pyridine, 2,2-bipyridine, 9, 10, phenyltoluene, etc. These ligands have filled sigma orbitals called donor orbitals and empty pi orbitals called acceptor orbitals are called pi acid ligands or pi acceptor ligands or pi bonding ligands. These ligands always combine with transition metals in low oxidation states of -1, 0, and 1 and form complexes which are called pi acid complexes. One of examples of pi acid complexes is Z's salt. It is an important pi acid complex and was one of the first organometallic compounds to be reported. Pi acid complexes have two types of metal ligand bonding. One is ligand to metal sigma bonding and another is metal to ligand pi bonding. Let us go through bonding of Pt2 plus ion with ethene molecule in the case of Z's salt. In ethene molecule, each carbon atom is sp2 hybridized. Each carbon atom forms 3 sigma bonds with the neighboring 2 hydrogen atoms, and one carbon atom using its 3 singly occupied sp2 hybrid orbitals. One singly occupied 2pz atomic orbital remains unused on each carbon atom. The singly occupied parallel 2pz atomic orbitals of two carbon atom take part in linear combination LCAOs, forming 2 pi molecular orbitals. First is filled pi 2pz bonding molecular orbital and second is vacant pi star 2pz antibonding molecular orbital. The filled pi 2pz molecular orbital of ethene molecule overlaps with the vacant dsp2 hybrid orbital of platinum 2 positive ion forming Pt2 plus C2H4 sigma bond. On the other hand, the vacant pi star 2pz molecular orbital of ethene molecule overlaps with the filled 5d xz or 5d yz atomic orbital of platinum 2 plus ion, forming platinum 2 plus double bond ethene pi bond or back bond. Therefore, in Z salt, both sigma donation and pi back acceptance by ethene molecule is accomplished using its pi molecular orbitals. So, it is a pi acid complex. Comparison of pi acidity of various ligands. The pi acidity of various ligands increases with increase in the electronegativity of their atoms. The reason behind the increase in acidity is the decrease of the energy of vacant pi star molecular orbitals and make them more suitable to accept pi electron density from metal d pi orbitals. Some common pi acceptor ligands have been arranged in the increasing order of their pi acidity. Reason for maximum pi acidity of NO plus is that it is an excellent pi acceptor ligand due to the presence of its positive charge, whereas the pre-existing negative charge on cyanide ion increases its sigma donor property but also weakens its pi acceptor property. On the other hand, pi acceptor or pi acidic ligand form two types of bonding with metal d orbital. First, filled pi 2pz bonding molecular orbital which is formed by addition of 2pz orbitals of carbon atoms. Second, vacant pi star 2pz antibonding molecular orbital which is formed by the subtraction of carbon 2pz orbitals. Metal carbonyls or carbonyl complexes are the coordination complex compounds which are formed by the combination of carbon monoxide molecule with transition metal atoms. In these compounds, carbonyl acts as a neutral ligand. Metal carbonyls occur as neutral complexes as positively charged metal carbonyl cations or as negatively charged metal carbonylates. The metal carbonyls have direct metal carbon bond and therefore they are also called organometallic compounds. They constitute the most important and the most rapidly growing branch of coordination and organometallic chemistry. They are industrially important, so they are involved as reagent, intermediate, or catalyst in many important industries and in various chemical reactions of immense importance. Metal attached to carbonyl in two ways. That is, first is carbonyls to metal d orbital, which is called sigma bonding. In these metal has less electron density, so it accepts excess electrons from carbonyl. There is no effective overlap take place. Second is metal to carbonyl electron transfer, which is pi back donation. Here, metal already has sufficient electron density. So when carbonyl donates its electron density to metal, it donates this excess electron density back to carbonyl through its antibonding orbitals. This is also called pi star antibonding. Here, effective overlap between metal ligand orbitals take place. These rules: first, The name of compound is written as one word, but if it is in ionic form, then the ligands present in coordination sphere is written along with the type of ionic species attached to it. Example, if a cation is attached to it, then it is written first, then constituents in coordination sphere, and if anion is attached, then entities in coordination sphere and then the anion. Second, in the coordination sphere, the ligands are named first, but in alphabetical order before the name of the metal ion or atom. The numerical prefixes such as di, tri, etc., which indicate number of particular ligand, should be ignored. Third, oxidation state of metal atom is written in Roman numerals in parentheses next to it, without leaving any space between them. Here are IUPAC names of some of the complexes. The metal carbonyls have been classified in following three ways, such as on the basis of nature of ligands, on the basis of number of metal atoms present per molecule, and on the basis of charge on the coordination sphere. On the basis of nature of ligands, metal carbonyls have been further classified as homoleptic metal carbonyls and heteroleptic metal carbonyls. The metal carbonyls, which contain only carbon monoxide molecule as ligand, are called homoleptic metal carbonyls. Examples: tetranickel carbonyl, NiCO4, penta-iron carbonyl, FeCO5, hexachromium carbonyl, CrCO6, etc., and the metal carbonyls, which contain some other ligands also in addition to carbon monoxide, are called heteroleptic metal carbonyls. Examples are tetracarbonyl, hydridocobalt 1, and dicarbonyl, dichloro, rhenium 1. Metal carbonyls are also classified on the basis of number of atoms per molecule. These are polynuclear metal carbonyls and mononuclear metal carbonyls, whereas polynuclear metal carbonyls are further divided into homonuclear and heteronuclear metal carbonyls. Now, let us discuss these properties in detail. First, physical state of metal carbonyls. They are generally colored, volatile liquids or solids. Second, solubility. They are generally non-polar in nature and hence they are insoluble in water. Water is a polar solvent in accordance with like dissolves like property. Exception is octacarbonyl dicobalt, which is polar in nature. However, metal carbonyls are soluble in organic solvents such as benzene, ether, alcohol, toluene, etc. Third, magnetic properties. After studying magnetic properties, we shall be able to know that whether the metal atom is diamagnetic, that is, no unpaired electron, or paramagnetic, that is, have some unpaired electron. It also helps us to explain that why the metal atom needs to pair up. The metal carbonyls are generally diamagnetic due to the absence of unpaired electrons. CO is a very strong ligand and therefore it has a tendency to get pair up the valence electrons of metal atom in the inner orbitals. Thus, the metal carbonyls are low spin and inner complex orbitals. The metals with even atomic number form mononuclear carbonyls. Thus, all the electrons in the metal atoms are paired. In case of dinuclear metal carbonyls formed by metal with odd atomic number, the unpaired electrons are utilized for the formation of metal-metal bonds. There are different bonding modes of carbonyl which are categorized on the basis of number of metal atoms attached to it. Free carbonyl gives stretching frequency band at 2143 cm inverse. Terminal carbonyl that is attached to only one metal gives stretching frequency band in the range of 1850 to 2120 cm inverse. Symmetric mu2 that is attached to two carbonyl atoms symmetrically gives stretching frequency band in the range of 1700 to 1860 cm inverse. Symmetric mu3 that is attached to three carbonyl atoms symmetrically gives stretching frequency band in the range of 1600 to 1700 cm inverse. Now we are going to study the effects of symmetry in terms of infrared stretching bands. First is MCO6, in which all the carbonyls are same and symmetrical, so it will give only one band. Second is MCO5L, in which carbonyl which is opposite to L will show distinct peak at rest, two peaks for the opposite carbonyls. Third is MCO4L2, which exists in two forms, cis and trans. Trans isomer has all carbonyls identical as both the L aligned opposite to each other, providing similar environment to all the four carbonyls, whereas in cis isomer there is asymmetry generated in the molecule, leading to four peaks. Fourth is MCO3L3, which exists in two forms, that is, meridional and facial, which shows three peaks and two peaks respectively, due to asymmetry generated in the molecule due to the alignment of ligands as shown in video. In this module, you have come across, firstly, pi acceptor ligands and their ability to show synergism, secondly, consequences of carbonyl to show pi acceptor property, and lastly, classification of metal carbonyls on different criteria and some of their properties has been discussed.